so which is known as support vector machines. Okay, so support vector machine is another supervised learning method which is used for classification, regression, as well as outliers detection. So the primary task of support vector machine are classification, regression, and outlier detection. Okay, and most of the time support vector machine is used for classification, but for a few tasks, support vector machines can be used for regression and outliers detection. Now, what are the if we look at the merits and demerits of support vector machines, then we can see that it is found to be effective in high dimensional spaces. Okay, so if we apply the support vector machines in high dimensional space, then uh, it will be used effectively. It will effective in cases where number of dimension is found to be greater than the number of samples. Okay, so number of dimensions here means the number of feature dimensions. So this is found to be effective where the number of feature dimensions is found to be greater than the number of samples. Okay. Now it uses a subset of training points in the decision function, also called support vectors. So it is also memory efficient. Okay. So when support vector machines are used, so they are not used for all the training points, but for a subset of training points, so which are also known as the support vector. To define a decision boundary, so this subset of training points are found to be useful for support vector machines. So since we are not using all the training points or all the training vectors, therefore this is found to be memory efficient. Now the next merit of support vector machine is that it is found to be versatile. So versatile essentially means that we can use different kernel functions, so that can be specified for the decision boundary or decision functions. So common kernels are provided, but it is also possible to specify the custom kernels. Okay, so this is one of the major advantage of support vector machine, that we can use the kernel functions to map the lower dimensional feature space into higher dimensional feature space. So that is why this is found to be very versatile among other classification techniques. Okay, now since there are some advantages of support vector machine, also we have some disadvantages of support vector machines, and these disadvantages include: if the number of features is much greater than the number of samples, then avoid overfitting in choosing kernel functions, and regularization term is crucial. Okay, so that means here if the number of feature vectors or the number of features dimension is found to be much more greater than the number of samples, then we should avoid overfitting in choosing the kernel functions, and regularization term is crucial. So we will learn about overfitting, underfitting, and regularization so in the subsequent classes, but for sake of understanding, or for sake of know the support vector machines, so we just remember this statement, that if the number of features is found to be much more than the number of samples, then we can avoid the overfitting. SVMs do not directly provide probability estimations. These are calculated using the expensive five-fold cross validations. Okay, so this is another advantage of support vector machine, that SVMs do not provide probability estimates, but we can calculate this using our expensive five-fold cross validation method. Now, if we look into the basic features of support vector machines, then uh, support vector machines define optimal hyperplane for linearly separable patterns. Now, if we get the feature vectors or the patterns, then we need to define a linear separable hyperplane or linear separable classifier. Now, Mm, this is one of the prominent features of SVM, that SVM provides, or SVM can define the optimal hyperplane for linearly separable patterns. Now, if the patterns are not linearly separable, then what we do? We extend to patterns that are not linearly separable by transformation of original data map to the new space. Okay, so if the patterns are not found linearly separable, then we get the optimal hyperplane by transforming or mapping the original input data to a new feature space, and this is done using kernel functions. So using the kernel function, we can map the lower dimensional input feature vector into higher dimensional feature space. Okay, and this is done by kernel function. So this is another prominent feature of support vector machines. Now, if we try to understand that how SVM works, then let us imagine that we have two different sets of data points. Okay, so one set of data points are labeled by blue color, and another set of data points are labeled by red color. Okay, so shape of one set of the shape of data points that belong to one class is found to be circle, and another data points are found to be triangle. Okay, now our objective is to get a classifier so that that classifier can linearly separate these two sets of data points that belong to two different classes. Okay, so here we can have two different features. Okay, so x and y features. So x and y, let's say this x and y are coordinates. Okay, so first we plot these points. So these points means the circles and triangles we plot in the xy plane. Okay, and then we try to find a classifier that will classify these two classes. Now what we do, we get a hyperplane. Now what this hyperplane means? This hyperplanes means the support vector machines is used to find the best hyperplane. So that means the support vector machine generates the hyperplane that best separate the two different sets of points belong to two different classes. Now this line is the decision boundary. So here you can see that the decision boundary is found to be linearly separable. Okay, so this line is the decision boundary, and anything falls to one side of it will classify as blue, and anything that falls to the other side as classified as red. Now, what exactly is the best hyperplane? Okay, so what is best hyperplane, or what is hyperplane? Now, now from SVM perspective, it is the hyperplane that maximize the margin from both the data points, or both the sets of data points. Okay, so in other words, the hyperplane whose distance to the nearest elements of each class is found to be largest. Okay, so here you can see that. So if between these two classes, so to separate these two sets of points belong to two different classes, we can have a number of hyperplanes. Now which hyperplane provides the optimal result or optimal classification, so that to be decided by the support vector machines. Okay, So first support vector machine define a classifier as hyperplane. Then if we have more than one hyperplane, then support vector machine has to choose a best hyperplane. So best hyperplane means that maximize the margin from both the points, from both set of data points. Okay. So in this example, here we can see that there are two hyperplanes that we have found, but we are taking the optimal one, which is called the best hyperplane, and this best hyperplane we are choosing due to the due to its due to the margin that has been found to be maximized from two examples that belong to two different classes. So here we can see this blue circles. So blue circles is found to be in one class, and this red triangles are found to be in another class. Now if we get a distance from this blue circle to this hyperplane and this red triangle to this hyperplane, that means this red triangle and this blue circle are found to be close to this hyperplane. So that is why we are getting the distance from these 2 points, okay, from which are obtained from two different classes. So this margin should be maximized. That means margin between, if we get a straight line, another straight line, two straight lines. So first straight line which is going through this blue point will be called the class margin for blue points. And if we get another straight line which is parallel to this hyperplane through this red triangle, then this will be called the class margin for the red triangles. Okay. So between these two class margins, we have to maximize this distance. Okay, and this best hyperplane will lie somewhere between these two class margins, somewhere middle of these two margins. Okay, or two class boundaries. So in this way, we can get the best hyperplane using support vector machines. Now, if the patterns are not found to be linearly separable, okay, then what we do? So we also get a hyperplane, but that hyperplane is not a linear hyperplane. So that hyperplane will be non-linear hyperplane. Okay. So for example, here we can get that blue circles are found to be concentrated near to the origin, and other red triangles from another class are found to be surrounded to this blue circles. Okay. Now to separate these two sets of points of two different classes, so uh, if we define the separating hyperplane, then the separating hyperplane would not be a linear, but rather it would be a circle. Okay. So that means the nonlinear hyperplane we need to define for this classification. Now let us talk about linear SVM. Now, if we consider a dataset of a number of observations, and this span a feature space V equals to Rx. Okay, so here V is the feature space which is given by Rx. So here Rx defines the feature space V. Okay, and here X is the set of observations. And if we get the absolute of X, that means this absolute of X defines the dimensionality of this feature set X. Okay. Now in this feature space V, the SVM identifies the hyperplane that maximizes the distance that exists between itself and the closest two points. That means here, if we define a hyperplane or a classifier, then the distance between the closest points from two different data sets or two different points, is, to be maximized. Okay. So some points here you can see some points may be found to be misclassified. If they are found to be misclassified, that means some points from class one class to be found in the region of another class, and some points from another class will be found uh, uh, in in the class from which we get the points in other class. Okay. So if we say this is the class C1 and this is C2, then if there are some points which are found, that means the points from C1 class are found in C2 class region, or some points from C2 class are found in the region of C1 class, then we cannot define a linearly separable hyperplane. So in that case, we need to we need to use the kernel to map the input feature space uh, into some other feature space. Okay, that means lower dimensional feature space will map to the higher dimensional feature space, and then we define a linearly separable hyperplane. If that exists, if that hyperplane cannot be defined, then for that patterns we need the nonlinear optimal hyperplane. But in this case, here you can see that the uh, here we can here we have two different sets of data points. Okay, and through these patterns we get a optimal hyperplane. Now our objective is to get the maximum margin between uh, two sets of points, and this hyperplane will be found at the middle of this margin. Okay, that means if we get the distance from one class boundary to another class boundary, so in between that class boundaries we will have the hyperplane. So at the mid of the class boundary distance we will get the optimal hyperplane. Okay, and uh, from both the class boundaries we will have the equal distance to this hyperplane. Now if one such hyperplane exists, then we can say that the observations are linearly separable in the feature space. Now, if we see the observations or if we see the patterns, then all the patterns are not found to be very informative. But there will be some patterns which are found to be very informative observations. Okay, so we can classify the observations into two different groups. One is the non-informative observations, another is informative observations. Okay. Now, in this set of 2 points, okay, two data points, then here we can see that these points these points are found to be the square the this blue color square. Here you can see that these blue color squares are found to be informative observation, and rest of the observations are found to be non-informative observations. Now why these are found to be informative observations? Because when we will define an optimal hyperplane, then through these observations we will get the we will get the class boundaries. Okay, so there will be two class boundaries for two different classes, and middle of these two class boundaries we will get the optimal hyperplane, or SVM will define the optimal hyperplane. And between these two uh, subsets of informative observations, so we will get margin. Okay, so our objective is to maximize this margin as much as possible, so that we can get the equal bias in favor of class 1 and in favor of class 2. Okay, and these informative observations are called support vectors, because these support vectors will help us to decide where the separating hyperplane to be placed. Okay, so we can get more than one hyperplanes, but all the hyperplanes are not found to be very optimal. Now if we take this informative observation through which the class boundaries are passing, then these informative observations will help us to decide among n number of our hyperplanes which will become the optimal hyperplane. And having the optimal hyperplane means that hyperplane decides the maximum margin to be found between these informative observations. So if any pair of observations belong to two different classes, then the hyperplane lies somewhere between them. Okay, somewhere between them. Now, as I said that we can have so many hypotheses, more than one hypothesis. So here hypothesis means the hyperplane separating hyperplane that will separate the two different classes. Now, these informative observations support the identification of the decision boundary. Now, support vector machine has to define a decision boundary. Therefore, which decision boundary will be found to be optimal? So that would be decided by the informative observations. Okay, and for this reason, we call these feature vectors located in the proximity to observations of other classes as support vectors. Okay. So here you can see that there are three hypotheses or the three hyperplanes. Now among these hyperplanes, we can get one such hyperplane, but before that we need to define the decision. We need to a class boundary, and on class boundary these informative observations will lie. Okay, and between these informative observations, somewhere in the middle of this margin we will get the optimal hyperplane or optimal hypothesis, so that optimal hyperplane become the classifier. Now how to get the decision boundary? So here we will go through some measurements so that we can understand how to get the decision boundary using support vector machines. Now, from linear and discriminatory function, we have obtained that if gx is the linear discriminant function, then gx is given by wx plus b. Okay, wx plus b, and here w is the weight vector. Okay, and this weight vector is nothing but weight vector is normal to this hyperplane. So if the equation of the hyperplane is wx plus b equals to 0, okay, then this w is the weight vector, and this weight vector is found to be normal to this hyperplane, and b is the bias. Now what is bias? So bias in this bias will decide where the hyperplane to be located, where the hyperplane to be placed. That means the location of the hyperplane is decided by this bias, and the orientation of the hyperplane is decided by this weight vector. Okay, so here we are writing uh, w uh, w transpose x, or this is also okay. So we generally write w transpose x plus b equals to 0. Okay, so here we have written x transpose w plus b equals to 0. Okay, and if we get the dot product, then this transpose should not be written. So in that case we will write w dot x plus b equals to 0. Okay, so as I said that the informative observations are found the class boundary. So here we have two-dimensional data. Okay, x1 and x2, and this observations, initially we get the observations to be plotted in this xy plane. Then uh, we get the class boundary. Okay, and then we get the optimal hyperplane. Now from class C2, here you can see that only one point is found on the class boundary for class C2, and for class C1 there are 2 points. So these 2 points means two green points are found on the class boundary for class C1. Okay, now this is the first point from class C1. This is second point from class C1, and this is the another red point from class C2 are found on the class boundaries. Okay, now these points are called the support vector because these support vectors are informative observations, and rest of the observations are not informative observations. So they are called non-informative observations. And if we get a margin between two class boundaries, then this margin is called this margin is to be maximized. Okay, so we have to maximize this margin between two class boundaries. Now somewhere in the middle of this margin we will get the optimal hyperplane, and this optimal hyperplane will be found parallel to both these class boundaries. Okay, so that means if we change the location of these support vectors, that means this will changing the support vectors will affect uh, the orientation as well, affect the location of this optimal hyperplane. That means if we don't get if we get this if we get these support vectors to be deleted, let's say we are deleting this support vector. Okay, we are not getting this point from class C2, and we are not getting this uh, green points from class C1. Then we have to change the class boundary, and new class boundary will pass through these 2 points. Okay, these two red points. That means the bias will be, and if we retain the optimal hyperplane at the same place or the same location, then what will happen that we will get the large bias in favor of class C2. That means in favor of class C2 of red points. Okay, if we if we remove this uh, if we remove these red support vectors, okay, that means we have to define another class boundary. Okay, and if the class boundary if the class boundary passes through this new support vector, that means this passes through these red points, then these red points become a new support vector. That means, and if we retain the position of the optimal hyperplane, then there will be a large bias in favor of class C2 of red points. Okay, but there will be a small bias in favor of class C1 of green points. So we do not expect the optimal hyperplane to be placed in such a uh, in between the class boundaries. Okay, in between class boundaries in such a place or such a location. So we have to, when we change the when we remove the support vectors, or when we get a new points which uh, which crosses this class boundary. Okay, and coming inside the margin between two sets of data points, then we have to change the class boundaries as well as we have to change the optimal hyperplane. Okay, so here you can see that here you get two one red points in the region of class C1. Okay, so this is to be misclassified. Now this will give the misclassification error, and this error will be added to the overall error, and we will get the error to be error getting increases. Okay, if there are any misclassification to be found, then so for those points we will get the misclassification error, and that error will be added to the overall error. Okay, but if the misclassification is not happened, then we will get the margin to be maximized. Okay, and in between in the middle of the margin we will get this hyperplane, optimal hyperplane. Now, if we have a pair of parallel hyperplanes, then that can be expressed by this expression. So, W transpose X plus B equals to plus minus 1. Why plus minus 1? So we are we know that the equation of the hyperplane is W transpose X plus B equals to 0. Okay. Now what will be the equations for these two class boundaries? So class boundary for green points and class boundary for red points. So if we consider these two class boundaries along with this optimal hyperplane, so we have to define three hyperplane actually. Okay. So for the optimal hyperplane of the separating hyperplane, so we will get the equation as W transpose plus B equals to 0. But what will be the equation for class boundaries? Now, if we consider the positive, these green points belong to the positive class, okay, and these red points belong to the negative class, then for positive then for the positive class, the support vectors will be found on the class boundary for class C1 of green points. Okay. Now, since these support vectors are found on the class boundaries, therefore we need to get this. We need to get the equation for the class boundaries. Okay, and these two class boundaries will be these two class boundaries will be found to be equivalent to parallel to this optimal hyperplane. Okay. Now here W will give the normal direction of the hyperplane and B is the scalar. And only since only the hyperplanes that can separate the two sets of points are considered, so we need to satisfy the conditions. What are the conditions? The condition is that W transpose Xi. So if Xi is any feature vector or a pattern, then WTXI and W transpose XI plus B is found to be greater than equals to 1 for I belongs to positive class. Okay, positive class, or we can say the positive class of green points. Okay, and in another condition, here we get the W transpose Xi plus B less than equals to minus 1 when Xi belongs to negative class of red points. Now, when you combine these two equations, two conditions, then we can write yi into w transpose xi plus b greater than equals to 1. Why we are writing this? Now, since there are n number of patterns or n number of feature vectors which have been plotted on xy plane, that means n number of patterns means if we use the n number of patterns or n number of feature vector for training the support vector machines. So for n number, we will get xi and yi. Xi yi means since support vector machine is a supervised learning method, therefore we will get feature point as well as we will get the class information. So class information is already provided with each feature vector. So we using the feature points and the corresponding class level, we will train the support vector machines. Okay, and here we are getting two different conditions for positive class and negative class, and then we are combining these two different conditions and we are getting yi into w transpose xi plus b greater than equals to 1. Why we are writing this? Because W transpose Xi plus B, when this W transpose Xi plus B is found to be positive, then this becomes positive and the corresponding class level will also become positive. So these two positive will give us the positive result. Okay, and if the feature vector xi is found to be in negative class, then w transpose xi plus b is found to be negative. The corresponding class level yi is also found to be negative. So if we take both the negatives to be multiplied, then we will get the positive. So that is why we are writing yi into w transpose xi plus b found to be greater than equals to 1 for I equals to 1 to n plus 1. Okay. Now, how can we find the optimal separating hyperplane? Now, in this uh, in this uh, in this diagram, here you can see that there are some non-informative observations and some informative observations. So, informative observations are found as support vectors, which are found on the class boundaries. Okay, and non-informative observations are not found on the class boundaries. They are found beyond the class boundary. That means they are found in their own respective class regions. Now, if we get distance from any such non-informative or informative observations to the hyperplane, then we have to find the distance. So let us consider this is the non-informative one such non-informative observations from C2 class. Okay. Now from this point we will get the distance to this hyperplane. Now how this distance to be defined? Okay, so from each such informative or non-informative observations, we will get the distance to these optimal hyperplanes. And for that, what we do, we uh, we calculate the distance by using the equation of hyperplanes. So what is the equation of hyperplanes? We know that W transpose X plus B, W transpose X plus B, if we consider this equation, W transpose X plus B equals to 0. Okay. And let us consider here xi, W transpose xi plus B equals to 0. So here we get the xi is some non-informative observations from class C2 or class C1. Okay. So in this case, how to get the distance? So we get the distance as W transpose xi plus B divided by root under W square. So here, if we write ax plus by plus c equals to 0, okay. Now there are two points x, two coordinates. Let's say x and y. Okay. Now with x we can find the coefficient a. With y we get the coefficient b. Okay, and c is, let's say c is the intercept. Okay, so we are writing ax plus by equals to by plus c equals to 0. Okay, now to get the distance, what we write, we get ax plus by plus c divided by root under a square plus b square. Okay, so similarly here we get W transpose xi plus b equals to 0. So we get the distance from any non-informative or informative observations as W transpose xi plus b divided by root under W square. So W is the coefficient of x. Okay, and here another coefficient is found to be 1. Okay, actually W transpose I plus W transpose xi plus b divided by root under W square plus 1 square. Okay, and W square. Okay, so W square plus 0, here coefficient for the next term is found to be 0. So therefore in the denominator we will get root under W square. So root under W square means W. So the distance between the two parallel hyperplanes is found to be d equals to 2 by mod of w. Okay, 2 by mod of w. So here the given any endpoints belonging to two classes, so we can formulate the finding of the optimal separating hyperplanes will be given given linear constant QP problem. Okay, so constant optimization problem actually. So here we get the f of w comma b equals to half of mod of w. So mod of w here we can write. So if we take half of w square, then w square can be written as half of w transpose w or w dot w. Okay, and this is the optimization, and this is the optimization function. So f of w comma b. So here w and b are found to be w or b are found to be model parameters. Okay, and we have to estimate these model parameters by training. So when we will perform the training with n number of observations, so this n number of observations will be used to estimate this weight vector w and bias b. Okay, and when we will do the classification with some unknown pattern or unknown observation, so we will use this weight and bias with that unknown feature vector and get the class information for the unknown sample. Okay, now here we have to minimize the weight vector w and maximize the bias. Okay, so therefore this is the constant optimization problem. Why it is constant optimization problem? So we have to minimize the w, we have to maximize the bias subject to this constant. So we have found this constant in the in this in this equation. Okay, yi into w transpose xi plus b greater than equals to 1. Okay, now we have to minimize this constant optimization problem subject to this constant. Now to minimize and maximize the w and b respectively subject to this constant, so we have to transform this constant optimization problem into unconstant optimization problem. This is also called the dual problem. Why dual problem? Because here we are estimating two different model parameters w and b. Okay, and subject to this constant. So that is why this is sometimes called the dual problem, dual constant problem. Now here we derive the dual problem to the linearly constant optimization problem, which is the one that is actually computed in practice. So we also give the conditions for judging if a solution is optimal or not. Now here now to get the solution or to estimate the weight vector and bias, so we can use the Lagrange multiplier. Okay, so Lagrange multiplier can be associated with this constant expression, and we can define the Lagrangian to solve this to solve this dual problem to this linearly constant optimization problem. So we can represent or we can express this constant optimization problem in terms of Lagrangian. Okay, now here we are writing L of w comma b comma alpha. So here alpha is the Lagrange multiplier. Okay, now where we are associating this Lagrange multiplier, here we are getting the Lagrangian as half of mod of w square. Okay, mod of w square minus summation over alpha I yi. So here you can see that this alpha I is multiplied this uh, with this constant. So what was the constant? So this was the constant yi into w transpose xi plus b greater than equals to 1. Now here when we write the constant, so we will not write this greater than equals to, we will simply write equals to 1. Okay, yi into w transpose xi plus b equals to 1. So this w transpose the yi into w transpose xi plus b equals to 1 denotes the class boundary. Okay, so we get the equation for hyperplane, optimal hyperplane is w transpose xi plus b equals to 0. But for two different class boundaries or two different parallel hyperplanes to the optimal hyperplane, we will get yi into w transpose xi plus b equals to 1. Okay. So we are multiplying and equals to 1. And if we take this one on the left hand side, then this will become this entire term minus 1 equals to 0. Okay. So here we are taking this, and if we multiply this alpha I with this constant having two different terms, then we will get this uh, summation over alpha I yi into w transpose xi plus b plus this summation over alpha I, and here I varies from 1 to n. Here n means the n number of observations or n number of feature vectors. Now here we have to, as I said that we have to minimize the w and maximize the bias. So therefore uh, we have to find the gradient. Okay, we have to optimize this function. We have to optimize this Lagrangian expression in terms of w and b. Okay, now to find the extrema for w, so extrema for w or extrema for b, what we will do, we will get the partial derivative. So we can write del L divided by del W for getting the gradient for W, and for getting the gradient for B, so we will get dl, we will take the partial derivative with respect to bias B. So for the first time, we will take the partial derivative with respect to W for getting the gradient for this Lagrangian expression, and then after having the gradient for W, we will get the gradient for B by defining the partial derivative dl del L divided by dB. Okay, del B. So this will give us the two different partial derivatives, and these two different partial derivatives will equate to 0, because we need to estimate the weight vector and bias from this Lagrangian. Therefore we need to get this extrema, one for weight vector, another for bias. See here we are doing so here alpha. So alpha will be defined for n number of, that means whatever the number of patterns will be found on the xy plane. So that many as Lagrange multipliers we have to consider, and here every Lagrange multiplier should be found to be greater than equals to 0. Okay, so the Lagrange multiplier should not be negative. It should be 0, but it should not be negative, or it should be greater than 0. If you have any questions, you can ask me. Otherwise, we will continue this discussion in the next class. Okay. Any questions?
No, sir.
Okay. That's all for
Thank,
today.
thank you, sir.